Okay, so like I said, so we've been talking about accumulation. So now we're transitioning to what's called accumulation function, and that's what you were doing with your homework. And so let's talk all about that. So many of you have heard in calculus, if you haven't had it before, this thing called integration. So let's as we develop this thing called integration, let's make sure we have the main idea firmly in place. What is the main idea behind it? So we never lose sight of that, right? So we'll start getting into a lot of details here, a lot of mathematical intricacies, but you never should lose sight of the big picture. And the big picture is this, okay? This is the big picture, okay? That the value or total change of a quantity can be calculated in a certain way, and that's what we've been talking about, as a sum total of many little bits of change. And that's what we've been talking about accumulation. Things don't accumulate in the normal scope of things. Things don't accumulate in big chunks all at once, right? Things accumulate little by little. It may accumulate very fast, but even as things accumulate fast, they're still accumulating bit by bit at a time, okay? Okay, so the value or total change of a quantity can be calculated as the sum total of many little bits of change, and that's what we've called accumulation. Okay, so now let's introduce this idea of accumulation function. So an accumulation function is just a quantity function, okay? It's just going to track the value of a quantity, the amount that we have, the current amount that we have, but it's going to do it in a framework of accumulation, which is bit by bit change, okay? So it's going to, again, the accumulation function, it's going to track the amount of a quantity that we have, but it's going to do it in a framework of how that quantity changes bit by bit, okay? So remember taxes on X dollars of taxable income. So our input, so this is an example. We're actually, when we've been showing the two graphs, right? We've been showing the two graphs. The graph on the right was an accumulation function. It was showing the total amount of the quantity at any current value of X. Remember that? So whether that was taxes, so our right-hand graph in the tax, the input was the dollars of taxable income, and the output gave us the tax. You see? So the input was the number over here, the number of dollars of taxable income. The output of that function gave us the total tax due on that. Remember? But now, as an accumulation function, how will it calculate that? How will it calculate that amount of tax? As an accumulation function. I know Christian knows. Anybody else? Kaylin, how will it calculate that total amount of tax if it's an accumulation function? Okay, Ryan.
Bit by bit.
Bit by bit, right? So it's going to be the sum of little bits of tax, too. And that's what we said. So getting the total amount of tax at a current amount of taxable income, as an accumulation function, it will be calculated by the little bit of tax on the first dollar, the little bit of tax on the next dollar, all the way up to the current dollar. Same with the height of the ball after X seconds. So the accumulation function takes X seconds, gives you the current height of the ball. As an accumulation function, how does it do that? Yeah, no.
I was going to ask a question on something else, but since the change in tax is equivalent to the rate of the change in X,
Right.
could you also write that as that for
Each one of those is, right, she's saying, if we have constant rate, each one of those can be written as rate times change in X, right? That's what we worked on last time. That's exactly right. Each one of those little accumulations of tax can be written as, at a constant rate, K delta X, K delta X, K delta X, absolutely. Okay, what about the height of the ball after X seconds? So the input is the current time, the output is the height of the ball. How would we express that as an accumulation function? Or how do we build that function in the framework of accumulation? Yeah, Chloe. Yeah, it's going to be the sum of lots of little changes in height up to the current value of X. So this is kind of our, yeah, sorry.
Can you specify like how small the change is when you're doing a function?
Yeah, so that's kind of what you did in your homework. So the change that you're using to get these changes in the quantity is you can vary it. You can vary it. We'll talk about that more today. That's right. Okay, other questions on this is the big idea, and this is what we'll spend the next couple weeks on. Again, so we're going to get into a lot of intricate mathematics, lots to remember, lots of stuff flying around. You got to have this big picture always in mind. This is what we're after. Okay? So you had this in your homework, right? And what was this? This function was? Yep, and was it the amount of bacteria, this function? It's the rates, right? So it was a rate function, so we could call it like RB of x. So the rate of change of bacteria. Was it hours? It's x number of hours? Okay, number of hours. Okay, so we've seen a rate function before. So for instance, our basketball. So remember what our basketball rate function looked like? Our rocket basketball? It was like this. Remember that? And we said that every half second the rocket fires and the ball suddenly is now traveling at a higher constant rate than the half second before, and then these rockets keep firing, and we get this kind of image of what the rate of change of the basketball is. Okay, so this one's sometimes negative, sometimes positive. And this one is always positive and increasing. Those are differences. But there's a big fundamental difference. So this was our rate. So for the rocket basketball as a function of x. Okay. So there's a big difference between RB and RB. So you have all the letters are the same. So what is the fundamental difference between this pink rate function and the rate function we worked on in the last couple of days? Fundamental difference. Christian?
That on RB, the rate is never the same. It's never constant. The rate of change is never constant.
So in this new one, he's saying the rate of change is never constant. Agree with that? So the rate itself is constantly changing. As opposed to in our rocket basketball, what does the rate do? Constant. And then it jumps to the next, and then it's constant, and then it jumps to the next, and then it's constant, it jumps to the next. Okay, so what are pros and cons of each? So we've got this rate function, which is always changing. As soon as you move a little bit in time, the rate is different. And this one is constant, different constant rates that it jumps suddenly from one to the next. So pros and cons of each one. Chloe?
Well, with RRB, it's not like practical, or it wouldn't actually happen in real life, but it allows them to calculate fairly accurately from that graph what the speed is going to be for like or what the rate is for every specific interval, whatever they want, they can find it really easy.
Easy to calculate. And easy to calculate what?
Is that one height?
Yeah.
Okay.
Easy to calculate delta H's, right?
Yes.
So we talked about how last time that there were these bombs in World War II that that were kind of like this. But to have a perfectly constant rate and then suddenly be at another perfectly constant rate is just physically impossible in our world. You just can't do it, all right? So the World War II bombs, kind of similar, okay? But she's right, totally not practical. What about how the bacteria changes? Realistic?
Yeah.
Yeah, so the rate could change, and it's going to do it continuously, right? It's going to do it gradually. Okay? And then she said, but then what about calculating how many bacteria you have at any given point? What about calculating how many bacteria you have at any given point? Easy or more difficult? Yeah, because you have a rate, but then as soon as a split second of time goes by, the rate's different. So how in the world are you going to calculate how much bacteria of change you had if the rate is always on the move, right? The rate is always changing. Okay? What about that in terms of calculating changes in height? Easy or hard? Every change in height equals constant rate of change. So the nice thing about this, what we call a step function, is the mathematics is very easy because we've got constant rate of change. Every change in height is just k delta x. K delta x. Okay, so does it make sense? So our goal is then, how do we get the accumulation for a function like this? Because this is what it's like in the real world. This is how the rate of something changes. This is a profile of rate that's realistic, whereas that is not. So you learned in your homework that what do? You use something like this to do it, right? So you actually create something like this in order to do it. And so I think what you had was, did you take intervals of 0.4? Is that right? Let's do 0.4. Okay, we're going to do 0.4. So we're going to take intervals of 0.4. So first interval was 0.4 here, and then what? 0.8, and 1.2, 1.6. We'll just go to 2, okay? And what did you do? So we broke the first, say, 2 seconds, 2 hours, up into intervals of 0.4 hours. And what did you do from there? Somebody knew. What did you do? Yeah, Ross.
We use the rate at the end of the interval.
Okay.
To account for the whole interval.
Okay, so did you use the right end of the interval for this one? So if we look at that interval, we're going to come down, and that's what I'm going to use. Okay, I don't remember exactly what you did in your homework, but so can I use the right end? Is that okay? So you found the rate at 0.4, and what did you say? For the whole first 0.4 seconds, what was the rate? That, whatever that was at 0.4, we're going to say that the rate was that value, and we'll estimate it at negative 500 for the whole time period. And then we look at this next 0.4 period, and how do we get the constant rate, the simulating constant rate for that 0.4? Alexander?
Just start at negative 500.
Start here?
I don't know.
Not sure. Okay. Jingrong?
Do you mean the second one?
Yeah, I want to do the second interval here.
I think the second one is negative 400.
And where are you looking to see that?
I am looking at the curve,
Okay. And which x value?
which has value 0.8.
0.8. So you're looking at the curve for an x value of 0.8.
Yes,
And then what?
it's about negative 200.
Negative 200. And then the whole interval we're going to say then is negative 200. Okay? Next 0.4. Tell me your name again.
Steve,
Steve.
well, you look at 1.2.
1.2.
On the graph looked on.
The graph.
Y-axis. And then, I don't know, about 200 or 150.
We'll say 150, okay? And then what? And then what?
Then you draw a line for the entire interval, like a step up from the next one.
And that's a constant rate of 150. Okay? And then we keep doing that. So 1.6 looks like about negative 50. It goes like that. And then at 2, is that about negative 400? And why are we doing this? What is the point? So if we have the rate function, why are we turning it into this? So is this rate function now, this new, what we're going to call a step function, we're going to call it step x. Is it the rate at which the bacteria is changing? Is it the true rate? Sterling.
No, it's not.
Is it close?
Sort of.
So, okay, good. It's yeah, kind of. It's based on it, but it's kind of not very good at all. So what's the point? Why are we doing it?
It's easier to calculate overall value, overall number of bacteria change
Why is it easier?
because you don't have a change in rate of change.
Okay.
Constant rate of change.
We can use so the reason we're doing this is now we've got something that we can actually calculate the amount of bacteria with, because we know the mathematics of constant rate of change, right? Okay. So let's just practice here. What is the value of step? I'm just going to just practice with the step function. Step of 0.7. Now, I don't want you to estimate a number. I want you to tell me, how can you represent? Where does that come from, that value? So pretend that you don't have any of these y values, okay? How can you represent step of 0.7? Ryan, want to try?
Yeah. You take the. Give me a sec. I know what to do. I just need to figure out what it says.
We just want to represent, yeah, okay.
Okay, so if you want to do step of 7, what you want to say is negative 500 of was that point times 0.4?
Okay, so let me make sure I got the question right. So you don't have any of these values. You don't know any y values. You just have the original function, the rate of bacteria function, and we want to just represent. We don't want to calculate a value. We just want to represent. Where does that value of step 0.7 come from? How can we represent it? Shannon. So here we are at 0.7. How could we represent step of 0.7? Which point on the curve? So how do we represent points on the curve? No, but it's a value, right? Step of 0.7 is some value. We want to represent that value. Where does it come from? Shana.
Yeah, is it RB of 0.7?
RB of 0.7. So let's look at RB of 0.7. What is RB of 0.7? We come here to 0.7, and if we're doing RB, then we're looking at what? Hold on a second. We're looking at that. That's RB of 0.7. So is that what step of 0.7 is?
No.
Okay, you want to try again? You got the right idea, but it's not RB of 0.7 because RB of 0.7 is down here. So it's RB of something else. Someone now. Kevin, were you going to chime in?
Isn't it just an arbitrary? Like, is that what we're doing?
No, step of 0.7 is the output of the function. It's a single value. Remember all that stuff we did with functions? That's the output of the step function when the input is 0.7.
Then is it RB of 0.8 because we're making everything in that.
Okay, here's 0.8. Oh, did I put R? Sorry, I put it in the wrong place. I'm sorry.
Yeah.
Yeah, if you see me make a mistake, speak up because it's going to happen. Here's RB of 0.7, right? Sorry. So you're saying it's the same as RB of 0.8. Does everyone see that? Where does that step of 0.7 come from? That value comes from the actual rate function at 0.8. All right, so what about step of 1.8? So just practice here. Okay, so you tried those. Step of 1.8, step of 2, step of 0.1. Go, see if you can do it. That's not 13, that's B.
Yeah, it's two.
Okay, Alyssa. Is that her name? Don't tell me. Ariana, sorry. So what about step of 1.8? What do you think? Okay, and how do you represent that? The same. Yeah. She wants RB of 2. What do you think? Is that right? That's it. All right. What about step of 2? Kenzie.
RB2.
Still RB2, right? That's where it comes from. All right. Janae, what about step of 0.1? RB of? Okay, so does this make sense? All our step function values come from, in this case, come from just 5 rate values from the original function. Any step function that any value of the step function that we would want in the first 2 hours is going to be one of 5 different values of the rate function, either r of 0.4, r of 0.8, r of 1.2, r of 1.6, or r of 2. Does that make sense? Okay, so now what about this thing about accumulation? So what was the initial amount of bacteria?
10,000.
10,000. So at 0 hours, so here we got x, and then we got number of bacteria. At 0 hours, there was 10,000. So what happened, according to our step function, what happened to the number of bacteria, according to our step function? How can you, Austin?
They go down by 500.
So we lost 500 bacteria. Agree with that? Marco, you agree with that?
I'd say so, yeah.
Okay. David, what do you think? The amount of bacteria went down 500 in those 0.4 hours.
I'm kind of thinking it's down 500 per increment.
So this is per what?
What is it?
24 hours.
What is the units on this value? What is the units on negative 500?
Bacteria. 500 bacteria.
Bacteria
Per hour.
per hour, right? These are rates, right? That's a constant rate coming from a changing rate. So does in 0.4 hours, if it's going down 500 per hour, is it going down 500 in this amount of time?
No.
So Nicholas, tell me instead, what is it? The change in
It's
bacteria is
negative 500 divided by 0.4
divided by 0.4?
times before.
Right. What calculation is that right there?
K delta x.
K delta x, right? So we're using constant rate. We're using constant rate of change to get a change in the quantity, right? So what is that? Thank you, negative 200. So according to our step function, after 0.4 hours, how much bacteria do we have according to the step function?
9,800.
Well, how much? 9,800. That an accurate value at 0.4 hours? Is it accurate? Is that how many bacteria there are at 0.4 hours? All right, is it more or less? Is our number of bacteria, is that value too big or too small? Aaron,
It's too small
why is it too small?
because if this is supposed to be a gradual increase to 0.4 hours, you should be losing at a rate of 500. That's way too less. That's way less than the amount that you have.
Okay.
Already.
So the amount of decrease you're saying was too great.
It's not. It's the amount that you're meaning is.
The amount of decrease. So the amount of decrease, that's too much decrease compared to the actual decrease. Right? Because we're assuming that the rate was 500, decreasing at 500 this whole time. When it started at 0 and it made its way, right? So that's too big of a negative number. You see? That's too big of a negative number. So he's right. That count of bacteria is too low. It would have come down less from 10,000 according to the actual rate curve. Does it make sense?
Yes.
Cool. All right. So that came from our change in B in the first 0.4 hours. So we just added the change in B, which was negative 200, right? All right. So at 0.08, so we can go faster now. How much is the bacteria increasing or decreasing according to the step function?
Decrease.
How much? How much did it decrease according to the step function? How would you, Elena, how would you get it? How would you get how much the actual bacteria went down over that 0.4 hours?
We should do negative 200 times is that 0.8?
So, but it's for starting at 0.4, ending at 0.8.
So 0.4.
Yeah. So again, K delta X. So you're going to take negative 200. The rate times the change in X, which is 0.4 again. And I think that is negative 80. So we'll have 9,720 again. And that's the second change. We're just adding delta B. So what are we doing? We're building an accumulation function. See this? We're building an accumulation function or a quantity function using this step function as the rates. Okay? What's going to happen in the next, according to the step function, in the next 0.4, will it go up or down? How much will it go up? 150 times 0.4. Is that 60? So it should be 9,780. Is that right?
That's supposed to be 1.2 to 0.6 for your X.
Yeah, thank you. Exactly. And then finally, so then 1.6 and 2.0. So every time, K delta X, K delta X. So now it's going to go down, what's this going to be? Times 0.4, down 20. So 9,760. Which is down 20. And then down 160. Again, so I'm getting 9,600. Check my math. Agree? So we can calculate these changes in bacteria using constant rate of change because we have constant rates. And the change in the quantity is K delta X. So this table then is an accumulation function. So this table right here, in the box in red, is an accumulation function of sorts. Okay, so it's giving us amount of bacteria at different points in time as it goes by. Kaylin, question?
What's the meaning of the change in B on the right side?
The change in the number of bacteria. So this is our bacteria count, right? So this, the output of this accumulation function is number of bacteria.
So the change would be, okay, I understand.
So remember, changes in Y are K delta X.
Right.
Changes in Y are K delta X. So we're using that principle with these constant rates to get each change. So that, like that first one was negative 200. And then, yeah. Other questions? Yeah.
So for the second portion, I guess,
Okay.
4.4
Right.
you put the rate as negative 200, but in the graph it's going up. So typically, wouldn't the rate be like a positive?
Okay, great question. So what she's noticing here is from here to here, the rate is increasing, but we've simulated it at negative 200. Peter.
The rate at which the rate is increasing is increasing, but the rate itself is still negative.
Okay, it's Peter saying that through in that interval, the rate itself is still negative. So what does the rate start in that interval? It starts at negative 500, and at the end of that interval, the rate is negative 200.
Yeah, but if you're calculating it, I'm thinking it, like, it's going to go, the number of bacteria is going to go down from the point at 0.04 to 0.08. So if the number of bacteria is going to go down, what is actually rising?
It's just
What's rising though?
It's rising, it's
Hold on a second. What's rising? Is the number of bacteria rising? Is the number of bacteria rising or falling here? No, because this, what are the Y values of this graph? But what do they represent? Rates, they're rate values, right? So all through here, the number, from 0 to 1, what's happening to bacteria? Decreasing in that whole time interval. It's just that now they're decreasing at a slower and slower decrease. Until now they start to increase. because the rate is positive. See that? Yeah, so you kind of got mixed up when you were kind of starting to see that graph as the quantity function when it's the rate function, right? It's the rate function. Yeah.
Does that mean that between 1 and 1.6 it's increasing even though it's headed downward?
She's asking, is the bacteria always increasing between 1 and 1.6 hours? So it's increasing through here, but the rate itself is slowing down. So slowing down, it's an increasing but slowing down, right? That's right. Good question. Okay, so we've got an accumulation function. How about it? Is it accurate?
Ish.
No, right? Because it's based on this very crude, it's a very crude simulation, right? This step function, we're trying to simulate the actual rate function, but with the intervals at 0.4, it doesn't do a great job, right? Because here the rate is much different than always being negative 400, right? And here the rate is much different than always being 150. The actual rate is much different than always being 150. Okay, so talk to the person next to you. What am I showing here? What's the same and what's different about this image? Go. What's the same and what's different? Well,
I think you're more accurate. You're off. Yeah, say like a whole 3 hours. It's still the same.
Every point
okay, so what is different? Molly, can you tell me one thing that's different about this one from the last one?
It's a rate function, it's just the time intervals are small.
Okay, so before we had time intervals of 0.4, now they're 0.1. What else is different? Jonathan? Anything else you see that's different?
well, if you're using the whole graph this time.
Okay, so instead of going up to 2, this step function goes all the way to 3.5. That's true? Tell me.
No, the line you're using to estimate each time is coming from starting on the left and then moving to the right versus going to the left.
So in order to get, say, so step 0.32. So where does that value come from? Step of 0.32. So how can you represent it in a different way? And yeah, Melody.
Are you trying to say when 0.31 starts and ends at 0.32? So you just want to rate that 0.31 starts?
I think you get the right idea, but we got our dimensions off here. So 0.32 is right here. How wide are these intervals? So we call that delta x, change in x. What are these intervals?
10 to the 9.
0.1, right? So now, not 0.01. You were thinking it was 0.01. So what would step of 0.32 be?
It would be for the one that says 0.3 and ends at 0.4.
So, okay, what one value is step of 0.32 though? So that's a value. How can we represent it with another value? Yeah. RB of 0.3. That's okay. Yeah, so now, like you said, now we're using the R value at the beginning or the left side of the interval. So this step function is based on left side. Now there's been a really, this is a really common confusion students have. They see, so students will look at this and they see the steps pointing to the right. So they say, oh, it's the right step. But it's not, it's the left step, because by saying left or right, we're saying which function value is the step based on? Is it based on the function value at the left end, or is it based on the function value at the right end? So which is it? Left. Okay? So don't look at these as flags pointing to the right and think this is step right. It's not. It's the function value that this is a very common mistake I've seen in the past. They look at this and say, oh, that's right, because they're all flying to the right. You see? No, it's which function value is that constant rate based on? It's based on the one on the left. Okay? So this is step we're working on left. Okay? Make sense? So what's step of 2.47? David?
RB 2.4.
RB of 2.4. Make sense? Okay. So, accumulation function, what do we have to do? We have to estimate all the rates, right? And then, for each tenth of an hour, we're going to use that rate to calculate k delta x and find the change and concoct a accumulation function. How about this? What do you think? Want to do this for homework? You did what, 0.4 and 0.2? You did 0.2? Okay, so this would be 0.1. And every time you make that interval smaller to create that accumulation function, it's just more and more work, right? Okay. And so then here's a graph of that. Very crude, okay, but that's based on that table that we just made. Okay, so conceptually this is fine, but it's way too much work, and it's inaccurate, right? We make some mistakes when we do that, and those rates aren't the true rates anyway, right? So what we want is we want to build up the mathematics so that we can have a machine do this for us, right? Because we know that computers technology is so exceptional these days, right? So if we can build up the mathematics and tell graphing calculator, right, to do the mathematics that we want it to do, we just click a button and it'll crank it all out for us, okay? So we want to use that to our advantage. We don't want to sit here doing all these problems where we're building tables, right, and doing this all by hand when the computer can do it for us, all right? But we have to tell graphing calculator the correct mathematics. So that's what we need to learn, is the mathematics behind this, so that graphing calculator can very powerfully create very good accumulation functions. Get it? So that's what we're going to do. Okay, so here are the steps. So we're going to take a normal rate function, and we're going to turn it into a step function. Why do we do that? Tell me your name again, sir. Stephen. Why do we turn the curvy rate function into a step function?
So you can approximate the rate of change in each interval.
Okay, and in order to?
So you can add these all
We're going to add the rates up?
each individual.
Okay. Sean. What's that? Average rate of change? We're not doing any average rate of change. So what's the why? So my question is, why are we making this step function? Make it a constant rate so that, Kaylin?
To add up the bits.
Add up the bits. Are those values the bits? No, those are the rates, right?
Right.
How do we get the bits? Yeah, tell me.
Times the change of x.
Right. So each rate times the change of x gives us that bit. Yeah, gives us that bit. And so then through that we can form the accumulation function. Okay, so every value of the step function has a value of r at the left end of the interval. Right? We said that? So step x is r of the left end of the delta x interval that x is in. We practiced a couple of those on the last slide. So what we need then is we need a method to get the x value of that delta x interval for whatever x value. So x, we talked about x increases, right? And so Boom, we stop at the current value of x. What we need is, given that current value of x, what's this value of x, right? Because that's going to give us the x value for which we'll have the rate, see? So coming along here, and boom, current value of x, right there. There's the current value of x. Given that current value of x, we need a way to get the value of x at the left end of the interval. So we need a mathematical way of doing that. Okay, so not here. Okay, so I haven't counted, so just pass them down. You're fine, thank you. Okay, so here's the setup. Just keep passing until, who doesn't have one yet? That corner of the room. So all the blank ones, get them to that corner. Thank you. So here's a graphing calculator program. So A is the starting value of x. Right now it's set at -1, okay? Then delta x is the width of our interval. Okay? And then the blue is the current value of x. So n, I can change n here, and that's the current value of x. Does everybody have one? Thank you, Kevin. We're good. All right, so here we are. The current value of x is 7.43. The goal is, given that current value of x, what's this value of x? So you've got this. You got the starting value of a, the width of the interval, and I want you to just how would you do this, right? So there's I'm not just figure it out. That's what I'm saying. So you figure out how would you get the x value. See, this is interval of the left side of the current interval. Okay, see if you can do it. And when you can do it, when you think you got it, raise your hand. When you think you got it, raise your hand.
What's the width?
0.8. A is the starting value. A is the starting value. So you can make this your first scenario, right? A is -1. Delta x is 0.8. What's that? Delta x is 0.8, and the current value of x is 7.433. So figure it out. How would you get the value of x at the left endpoint? It's a bad example. Too easy. Let's do this a little better. So let's do 0.82, and let's make a -1.3. So you can go on to the second one. We're not going to have time to do them all. So go on to the second one.
Can you explain the first one? I'm sorry.
This is a new example. Forget about the first one. It's the same.
So we erase the first one.
No, you just go to the next one. We're not going to have time to do 4 or whatever it is. Just go on to the next one. They're all the same. It's just different numbers, right? It's all the same thing. All right, so A here is, I'll start over. Sorry. A is -1.3. That's the starting value of x for the intervals. Are we good on that? Each one of these intervals is 0.82 wide. So we go 0.82 from there and then 0.82 to get the start of the next interval. The blue bar, or the n value on graphing calculator, is the current value of x. It's the current value of x. So we're coming along here and boom, we're at the current value of x, which is 6.37. I'm getting there. Okay, what's our goal? We need to know the x value of the left side of the current interval. We need to know the x value because we're gonna have this step function, right? And the value of the rate of change is gonna come from the x value of the left side of the current interval. So we want the x value of this point right here. Find it. Do whatever you can to find it, right? Figure it out. Do whatever you can to find that x value.
Yeah, that's what I'm doing.
That's a really long way
Aaron,
Is the answer 6.08?
I don't know. The process is more important. How'd you do it?
But I counted up the number of dots that it would take to get towards
Okay,
the answer,
you counted.
which was 9 dots, and then I multiplied it by the change of x, which was 0.82,
Okay,
which then resulted in 9.
so you had 9 times 0.82. And that's it. Is that it?
And then let's subtract that back from that 1.3.
And you start at negative 1.3 plus. What do we think?
Did you get 9 from this?
Well, I know there's 9.
Okay, so let's generalize this. It's a plus, what's 9? This is like the number of intervals. The number of, what, full intervals before the current interval, right? And what's the 0.82? Change in x. Does it work? Okay, so what if we don't want to count the number of full intervals? We need a way to get, Steve?
You just add 1.3 plus 6.37 and
Okay.
divide by your 0.82 to get the amount of intervals. Then you just do the same thing up there.
All right, so
Just get your 9.
tell me again, you want to do what?
We'll add 1.3 to 6.37.
I think you want to get you're saying the distance from
Yeah,
here
the
to here.
distance.
So in general, how would you get that distance? How would you calculate that distance from starting A up to the current value of x?
Well, whatever your x-axis, the length of your x-axis.
It'd be x minus A, right?
X minus A, yeah.
Be x minus A. Okay, then what?
And then you divide it by your rate.
Divided by
Your length of your intervals. The total
0.82.
amount of intervals.
All right, will that get it? Does that get it? It'll be close, but we want it exactly. Why does this not get it? What does this include that we don't want? What was that? Yeah, so doesn't that quotient then also include that little bit of extra? So what we want is we want to take that thing and say, give us the next integer lower. We want the next whole number lower. That's called the floor function. So we're going to take this whole thing and do this. And what that tells us is whatever's inside there, give us the next whole number below it. The first whole number below it. Or just chop off the decimal. This is called the floor function. Sorry, this is delta x. So it takes a decimal value and it just lops off the decimal, so it gives you the whole number before, and that will be the right number of intervals. That will give us 9 intervals, right? Okay? Any questions on that? Yeah.
How would it look if you wanted to see it on the right side?
What's that?
Like, you know how you're doing the left side? So
Yeah,
that's
let's
floor.
think about it. Let's talk about a different day.
So is it just up? How would
Oh yeah, so the ceiling.
ceiling?
But how could you do that same thing with using the floor function? Think about that. Okay. Thank you. Great class. Any question? Yeah. You don't need the parentheses. Is that what you're asking? Yeah. So you just perfectly good. You don't need the parentheses for the floor function. Once you have it. Floor function. Is this homework? What's that? Nope. Yeah. Bring this on Friday. Just bring this Friday, okay? So do more practice. So the x minus a over delta x.
We didn't count the little bit in between 6 and 6, or we didn't count 0.37.
No, because we're doing 6.37 minus negative 1.3. See? So we're doing 6.37 minus negative 1.3 all over 0.82. Why is that not going to give us the number 9, right? We want exactly 9 whole number intervals. So that will not equal 9. Why not? It's trying to equal 9, but it doesn't equal 9. You see? It's this distance.
Right.
Broken, divided up into the width of each interval. Should give us the number of intervals, right?
Right.
But that won't equal 9. Why won't?
Because we have a little bit more.
There's a little bit more, right? There's a little bit more there. And we don't want that little bit more. So this is really actually equal to something like 9 point, let's do it. So from here into 6.37 minus negative 1.3 all over 0.82. 9.3537.
Okay.
But what do we want it to be? See, that's 9.3537. Oops. Oh, like this. Does it go away? There we go. There we go. Okay. What do we want it to be? 9. So if we take what's called the floor function, if you apply the floor function to that, it just lops off the decimal and gives you the previous whole value.
Okay.
And that's what we want, because we want strictly a number of intervals. You see?
Right. Not the little bit.
Yeah, we don't want to say 9 point whatever times delta x, because that'll get us to there.
Right.
We want to get it to there. So we need the whole number less than that, which is what the floor function does.
Okay. Thank you.
Sure.
I was just wondering, are these brackets the same as that? Is it the shift that?
No, that's just a normal bracket. Like shift that, it actually gives like this. It's like a different kind of parentheses, right?
Okay. How would we get that?
Don't worry about it for now. Just know what it means. I'll show you. Yeah. Thank you. Those are today's. Hi. Let me turn this off.